I'm honored to be here. It's great to be here. This presentation has taken 44 years in the making to get to this point. I grew up as a Westinghouse ABB guy for 35 years, and I've been with Duke now 8.5. So I'm a newbie at Duke, which is interesting. And this is a problem that I don't want to stand up here and articulate problems that Duke has, but I think every company has this problem. Duke is aligned in generation, transmission, distribution, AMI metering, asset monitoring can be its own group. There's these different groups, and to get the cross-pollination is difficult. So I'll offer all of you, part of what I want to talk about today is kind of lessons learned a little bit and aha moments. So, yeah, I'm going to take you on a lab tour through Mount Holly. We'll go back to the history of our team just a little bit and go through some of the things that we've learned moving along. And then I'm going to talk about the importance of zero trust. So I haven't started the presentation yet. I'm telling you what the presentation is going to be, right? So zero trust, and then how it works and why it's important, aha moments. So people are still coming in. Are you ready to get started? You ready for the presentation? Okay. By a show of hands, how many of you in your head have a definition of what zero trust is? Looks like all of you. So I don't want to hear your answers yet, but when we get to the end, somebody tell me if my definition of zero trust matches what your definition is, all right? So, and how we got there. So this talk, Zero Trust Applications for the Grid, internally we call it ZTAG, I like the name. And what we've done is we've taken CI/CD, specifically Kubernetes, and we've overlaid it on top of a microgrid. We're getting ready to overlay it on top of a test feeder. We can go into the details of exactly how that works. Going through life, I've been looking for distributed PKI for a long time now, and I kind of ran into it. So let's get started. All right, so I live at the little red dot right here. The Mount Holly microgrid is where I hang out a lot. That place was built in 1968 or so. It's been around a long time. It's a training facility for a lot of the lakes that have been built, and the nuclear site in McGuire, and the Marshall steam plant, and it's been a training facility for a long time. The Emerging Technology Office, us, we moved in there in about 2015, and during COVID, we've put a lot of money into this place. So it's much nicer than it was. It's better than 1968 tables and chairs, right? Which is interesting. So this feeder is about 5 miles long. You can see we're at the end. We have 1.2 megawatts of customer solar hanging on the end. And yeah, we have all this equipment, and it hangs out there, and we live there. So here's the overhead picture of it. One point that I would like to make along the way here on distributed, we're really working on distributed intelligence. You know, the grid has been centrally managed, centrally controlled, big generation, but now with renewables, people call them DERs. If you're from the South, it's DERs. It's so much solar, wind, battery, all this kind of work is taking place. So the pendulum is swinging to more distributed systems. When I look at the microgrid here that you're seeing, you see 150 kW of solar up there, a lot of different stuff. There's 400 meters at the top for testing, 400 meters over here. Here's some solar. There's a new chunk of solar here that you'll see from me in just a minute that I've added. The campus runs, not all of it, but this building, which is where our main lab is, it runs as a microgrid. We're islanded 85%, 86% of the time. We're off the grid. If we lose comms, we continue to function. So it's a distributed autonomous function. And one more point on this, I really love these two units right there. They're from a company called Source. Everybody look this up. You know, some people may love it, some people may not, whatever, but it's a distributed autonomous function. There's two types of panels in this thing. One is a solar panel that runs a pump in the bottom. The other piece is a dehumidifier. It takes 4.6 liters of water out of the air and drives a little water fountain right next to it, which is, you can't see that one in this, but close. And so in a place where you have to walk miles to get a jug of water, it's a very nice thing. But my point on that is, it's a distributed autonomous function. I would ask this question to the group. We're running our microgrid that way. Why don't we run our cities that way, our buildings that way? Why don't we have that focus of abstraction layers on top of this thing? I don't want to micromanage everything on the inside of it. I want it to do its own thing, and then I'll put a nice, like a good object-oriented programmer, I'll put an abstraction layer on the outside of it. So just some pictures here of the lab. We've really fixed it up. It's a lot prettier. If any of you that are colleagues out there that have been to the lab and you haven't been recently, I invite you all to come to Mount Holly, North Carolina, 14 miles to the northwest of Charlotte is where we are. We're doing an awful lot of stuff here where you design a circuit with a schematic editor. This equipment is from a company called Typhoon. It's one of the fastest hardware-in-the-loop simulators in the industry. So if we want to design equipment and put it in the field, we run it in the simulator here, running on top of the real circuit that it's going to be part of. And then when you have hardware-in-the-loop type stuff, you can actually press the buttons on the devices. It feeds into the simulation, and there's a feedback loop going on all the time. So it's really nice stuff. This is Bay 5. I've built Bay 5 in the last year and a half. All the loads in here are DC. So this is essentially a DC microgrid, although we haven't provisioned the battery yet. You can see I have an e-bike. All the lighting is done with DC, 24 volt, 100 watts, per out of shade. All the monitors run off straight off DC. The point in this is 85% of the loads in your house today, and going up, your refrigerators all have DC motors. There's an AC front end on them. So if I have PV and I have electric vehicle or I have a battery, why do I go to AC only to go back to DC? You know? So we're getting rid of wall warts. It's my life mission before I pass out and die, right? Is to get rid of wall warts. Yeah, there you go. Hallelujah, brother. All right. So these wall warts. So you end up, I think the room of the future will end up having 240 is what Europe uses, right? 240 AC, RMS. So take 240 times the square root of 2, you get to 350 volt DC. So we have one plug, it's UL certified, it's from Anderson, it's a 350 volt DC plug, and we have those on the wall over here. I don't mean to talk about AC, so DC over here. That's that. Those guys are plugged into 350 volt DC. And then everything else is USB-C and USB-A type connections. And I think USB-C is moving up to 48 volts, kind of like in the PoE range, but I think PoE is capped at 100 watts, and USB is going to advance to 240 or so. That's coming. All right, enough of that. Let's see. Look this way. More about Bay 5 DC, just added 19.2 kW of solar, also a Coretech electric vehicle charger that is directly wired into a DC panel at 350 volt DC. So as far as I know, that particular charger, it's the only one I know in North America that's directly plugged into a 350 volt DC bus. Everybody else, what we did was, the version that we have there, there's no transformer in that. Most of those will have a vehicle-to-grid thing, has a big transformer in the base of it that weighs about 400 pounds. That does not have that. So anyway, that's enough about DC. This is a cyber conference. All right. One more thing that we're doing to the lab is we've added 1.5 miles of test feeder on the inside. This is kind of a lousy slide, but we added 31 poles in the last 6 months or so. We're getting ready to start commissioning in the next month. So the idea is to do distributed intelligence applications. So the idea is that I have different boxes out there, and they actually manage this chunk of the feeder distributed, not managing it from SCADA. You know, I don't mean to be sort of an anti-SCADA guy. I am a distributed SCADA guy. That's where we're headed. History of our team. So. Yeah, the years I did Westinghouse ABB, you know, I wrote code in meters for a long time, and then I took this job with Duke in this R&D group in 2013, and Rayford Smith told me, become a cyber expert, become a security guy. And I'm going, wow. So and that's why I'm intimidated by you guys, right? So one of the first things I just really realized is that the grid is like a coconut, and that it's hard on the outside and mushy on the inside, and we put firewalls everywhere. Now, I don't mean to put down firewalls, but I think we need to do zero trust and move on beyond this. In 2014, 2015, we were on stage at SANS with this setup right here. We had ABB microscale on one side of the stage, and we had this particular unit that's a mock-up of a substation. We broke in, we plugged in a Raspberry Pi, we watched the network traffic, we saw what's the right term? The controller, the RTAC on top, and then we saw very easily, just watching network traffic, we see what the outstations are. We did an ARP spoof. We took over the RTAC, and then we just pounded the protection relays with binary outputs, turn the power on and off. So we oscillate the power, and we burn, what I would really do is have 30 substations wake up at the same time, oscillate the power, and burn everything up, to the best of my ability. That's what I would do if I was one of these guys, right? But my takeaway from that was we have no cryptographic identity for these devices, and we definitely don't have encryption going on between any of them, so it's all clear text protocol stuff. So that was a big takeaway. At that point in time, we started working with publish and subscribe protocols. The idea of I'm the client, I'm the RTAC, or I'm the controller box, I'm the client, and all of you are servers, and I'm going, what do you got, 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 all day long, crunch, what do you got, what do you got, what do you got, crunch, and I do that all day. I would rather have you guys publish on a message bus that came out in the 90s with TIPCO and WebSphere and this stuff. MQT is fantastic, as is, you'll see in just a second, we've done work with DDS. We did all this exploring with TPM 2.0 chips to see how you can hide identity and hide keys. We deployed silent defense from Security Matters at the time in the lab, and I got a big aha on that, in that I have the one line looks great. We island, reconnect, KW adds up, everything's great. But the IT under the hood is really unhappy. NTP's devices aren't getting time. We have UPSs trying to go through our firewall to reach their mothership for whatever reason. You see all kinds of stuff when you use these kind of tools. It's basically Wireshark on steroids is what this thing is. We moved on to NATs. We love NATs as an application layer broker. I love this thing. It's fantastic. We can drill into that. So what we've done is we've overlaid a Kubernetes cluster on top of our microgrid. And it's got 6 nodes. We're getting ready to add a kube cluster on top of 9 of them on top of our test feeder is where we're headed. So what's the point in all this is to reach zero trust. So why? Why are we doing this? Today we have no cryptographic identity. It's kind of a bummer. To deploy and patch applications in the field, most of the time we have to roll a truck out to poles and boxes hanging on poles and in substations. It's very difficult to patch. We need better situational awareness. Duke has rolled silent defense out now to over 600 substations. So now we're not blind from beyond the gateway inside of substations. We're seeing this stuff take place. I think power systems engineers and all of us need to think in terms of abstraction layers and have a distributed autonomous function and put an abstraction layer on it that makes sense. A lot of the 61850 work over the years with semantic modeling, the work that we've done in open field message bus, all this is going after that. Distributed intelligence with a nice abstraction layer on top. And then the whole concept of, what do you do on-prem, what goes to the cloud? Quite frankly, is a big gap. The guys that are working in the cloud that can stand up 50,000 Netflix containers in a heartbeat, stand them up and make it go. This is an amazing world. There's a lot taking place. In our world, at the lower levels, we have power electronics work that's taking place. It's phenomenal. But the IT in this particular piece of the world, I think, is weak because we'll develop a great box, power electronics, does all kinds of cool things, and then we slap a 1978 Modbus stack on it, and that segment, whatever it's talking to, will never be secured. Not unless you do something really bizarre. So we're trying to avoid this. We don't want that to happen. So that's just a protection relay, right? That its boundary got set so high that it never opened. It should have opened, and it failed to open. The opposite of that would be set the boundary so low that it opens all the time. Every time you turn around, it's open and the power's off. So which one do you prefer? Has to be just right. So here's a picture. We've used, just for the nodes in a kube cluster, we've used these industrial PCs from a company, we've used industrial PCs. And so I've got one node that sits on top of that solar field up there and on top of a DC bus and some stuff. I've got a gas generator that's kind of a collection. The heart and soul of the microgrid is this piece. When we island, he takes over. This is an ABB inverter with a SAF 650 kW battery. We have grounding experiments going on. Here's the point of common coupling. When we open way 1, we're islanded. When we close it, we're back 1. And we have to pay attention to all this sort of stuff to make sure it operates seamlessly, of course. Another graphic of, you can see the kube cluster here overlaid on top of the microgrid. This is really overlaid on top of that hardware in the loop simulator, and we will overlay that on the test feeder as we move forward this year. And then what I've got running in the node orchestrator up here is all this open source tools, Everything we're doing in this is open source, by the way. And if you guys need access to any of it, we'll figure out how to get it to you, right? The idea that, the amazing thing to me is, let's say there's an app that needs to be a workload that needs to be deployed on one of these nodes. These nodes can run multiple workloads. I make a change in Git. I've tested the heck out of it. I changed the low-code, no-code declarative stuff. Fleet picks it up and informs the kube cluster, the K3s agent on each of these nodes, which you'll see here in just a second, to pull down the new node that it needs. And the way containers work is you bring in a new one, and there was a talk yesterday that was excellent. I mean, you bring in a new one and you want the old one to die, right? So there needs to be, studies on how to hand that off if there's data problems. That was mentioned in the talk. So, but anyway, this is the work that we're up to. And why are we doing this? So we can patch, so we can deploy distributed applications, so that we can have zero trust security. And we're going to hit on that now. Whoops. All right. So here's what a node looks like. So picture the smallest one I've got is a little CompuLab box. It's about this big, and it can run many, many, many Docker containers. And then, say a little bit bigger, like an SCL3360 or an OnLogic box, it's an industrial PC, basically, And I'm not trying to make sure that they're necessarily hardened for where we're going at this point, because the idea is to put a node on top of this stuff. So what we've done in the microgrid is, let's say there's 6 devices, 3 speak Modbus, 3 speak DNP3. We put a node on top of that, and we hide the legacy protocol. Now, we think we'll be able to do MaxSec in the future on these segments, but we hide the legacy protocol. And on the north side, we're publishing NATs, and we have, when the device first goes to the field, we have a TPM out here, and this Spire agent does attestation with the Spire server. In this case, we're going all the way back to the cloud, to our NOS, and is saying, yeah, you're a valid guy, you can go and work now. So we have trusted hardware and only trusted workloads. Each one of these is an application, or in the Spire world or the Spiffy world, these are called workloads. So you can see we have a PTP time server. We've got time series database. This guy is actually running the microgrid. He's doing the optimization of the microgrid. I could have 3 of those scattered across different nodes. Kubernetes can put them wherever and run a raft algorithm such that only one of them is doing control, but the others are listening, and if one dies, then the other picks it up, right? That's kind of a nice thing, and that's not hard to do. And then the real essence of these 6 Southside devices in the example I gave is this OpenFMB adapter. What it does is, it's an open source piece of software written by Adam Crane. It polls DNP3, it polls Modbus. That would be 6 workloads, actually, 6 adapters. Polls it, brings it back, turns it into an OpenFMB sort of 61850 data structure to harmonize data, which we all need in the world, harmonize the data, and then publishes. So at this level of the 6 nodes, they're all doing encrypted traffic. And each one of these guys has got it's a little bit fat. We're looking for something smaller. It's got an Envoy wrapper around each one of these. Because if you look at them, you call them a workload, but it's actually a Kubernetes pod. So it's wrapped with Envoy, and Envoy knows how to talk to the Spire agent. And so every one of these workloads is having their Leaf certificate in their little trust bundle refreshed by a Spire server that is running on another node in the microgrid. So what we've done is we've taken the intermediary CA concept, and we've put the CA in the microgrid. And that guy is signing for all the workloads. And we can do it every hour, we can do it once a week, once a month, whatever you like. But then the abstraction layer, the main Spire server is a federated guy, the one in the microgrid. He then, at a slower cadence, gets his certificate refreshed from the level above, which could be in the substation, or it could be up in the cloud, or wherever you want to put it. So, I'm not claiming to have the answer to everything in the world, right? I'm sure there are holes in anything that you can build. But in looking around for what's best practice coming from the cloud service providers and the lack of zero trust security in the grid, we built this. And it's all open source. It should go. If it's not this, I challenge you, what will it be? If it's not something like this, it will be something like this. And I really worry, a big worry, is that we get a really good security solution from one vendor, let's say. And then we're locked in. They're going to lock us in the full stack. And these layers need to be interoperable, And I'm not big. I don't think government should mandate, what free enterprise should do. But it's a little bit crazy in that we can't get a model that will protect us all, in the control system community. This architecture can run in factories. It can run on the grid. Any control system architecture. So another little view of it. I've got a node up here, and this node is really hiding these guys with multiple ports hanging off the back, and doing protocol translation, and then now we have another world. But really what we're saying is we would like this functionality that's in this thing to run ultimately in the edge device. So the Cognizant guy that was here this morning, that was a great talk. He's saying I can do all kinds of crypto and 8-bit micros. So what we need is a pub-sub protocol in the edge device, and we also need just the ability to refresh keys in the thing and to do all this securely. So it could reach, we want it to reach ultimately, not be a bump in the wire sitting on top of everything, but go to the edge device. So there are places where the bump is perfect. If the bump is a radio and today it's a pass-through device, it should be a more intelligent bump than just being a freaking pass-through radio. Come on, So let's see, where are we? I think that's it. So what are we getting? We're getting zero trust. My definition is cryptographic identity, that before I talk to you, Ben, we're going to prove who we are. Somehow, if I can't prove just with a direct thing, I'm going to do attestation somehow. But hopefully we exchange certs, and your cert and my cert have been signed within the same domain, so we trust each other, and then we can speak. Full MTLS is what we should be up to. Now, the protection guys are going to complain it's too slow, right? So we just need to tackle the problem and focus on it. There's ways to be slow and fast. There's ways also to design your world, your circuits and everything, to run as slow as possible. Put a control system on top that just runs as slow as possible. Figure that out, So we just need to think about it more rather than just saying no. So we can patch, situational awareness. We really need to drive to interoperability. These are all the things that we can get from a system like this. So I think that's it. So what are we in the business of? We're trying to keep the lights on, And that's my sleeping dog. Yeah, all right. So we got 3 minutes. Whew. Thanks for listening. Please, questions. Let's talk about this stuff. Anybody? If I can't answer it, I'm gonna ask you to call Dwayne Bradley in Mount Holly.
Hey, David, thanks. Great presentation. Complexity is sometimes the enemy of security. Would you care to just point at anything you think might be too complicated in any of this, or is not a worry?
Well, getting the TTL right, when you're doing CSRs really quick and getting things re-signed, what happens if you get stuck? We haven't done this yet. We haven't said a storm came through, this thing is dead for 10 days. What is the technique for bringing it all back online? I see that as a complexity weakness. If we can't solve that, I don't think it's a hard problem to solve, but we just haven't done that one yet, But that's one that I think is key, right? What happens when things don't work? And if you ever wrote control system programs in your life, 50% of it is error handling. It's at least 50% is when things don't go right. What do you do? Next one.
Yeah, you talked about this as maybe like a future work, but how are you authenticating the endpoint devices, like the IEDs and that type of stuff?
We're not really, not in this case. We've put a bump in the wire on top of them. Now, the solution that I've seen that has existed for a long time is this thing called MACsec. Okay. We haven't gone to the trouble to use, in this container system running on a node, right? I could put a copy of a fat client software that knows how to talk to that particular device. This is how I would do Southside patch management in a legacy environment, right? But have we gone in and tried to read stuff out of it to identify that it's the correct one? No, the system's prone to weakness. If you pull that edge device out and put a new one in that's a clone, but it's a bad clone, no, you can do that. But the MACsec piece secures that last 3 feet of Ethernet, and the way it does it is somehow when they come alive, they do a bit of identity, I believe, or at least there has to be the MACsec algorithm in there, and they start with a symmetric key, and then they can renegotiate throughout life new symmetric keys. So this last 3 feet of Ethernet is a symmetric key thing. That's called MACsec. It came out of the telecom space with Cisco and all this. But nobody that I know of has implemented this in the industry yet.
But by default, that's a shared key.
Say that?
MaxSec uses a shared key by default.
Shared key, but I thought they can rotate that key during an encrypted session.
You can, but you've got to do things like have a discrete separate key for each link,
Yes.
right? That type of thing.
Yeah, but you know, the bad thing about security is, or the good thing is, I mean, it has to be seamless and hidden, you know? That has to work. But I am advocating this. Okay, most of the time we have a box, and I'm willing, for this next step, I'm willing to give up that last foot or so until the stuff we're talking about ends up in the edge device.
So one thing, if you don't mind.
Please.
What is the mapping between this bump in the wire and the endpoint devices? Is it one to many, or?
It can be one to many. One to one, if it's a radio on a pole, that's pretty typical one to one, you know, a recloser in the field, or one to many in the microgrid case.
Okay.
But the work we're doing at the container level is to say, we don't necessarily have to take containers to the edge, but the work that we're doing there, at least a couple of the pieces of it, should go into that edge device. Quite frankly, I'm burned out on DNP3 and Modbus. 1978, 1991, it's all we know how to do, I guess. All right, anything else? Oh yeah, sorry.
Just one last question. David, in the implementation of these boxes, are they double NIC devices where you've actually isolated the thing that you're protecting?
We've done both. We've plugged them all into a switch. That way we can run the old system that pulls everything, and then we can switch and run the new system. And so, but everything's going through a switch. That's one. Now we have done, the on-logic boxes happen to have 4 ports. So 1 to 4 in that case, right? So it kind of depends, but we're still in, I mean, it's not a deployed, it's deployed. It's a real system, it works. You can come to Mount Holly and see the one line and all the stuff running, but it's, you know, we're not selling it. It's not product ready for sure.
Understood.
But the challenge is, please, let's build a system like this. Or what are we doing in this country? You know, if we're not building something like this. We're just hiding behind firewalls, is my view, you know. This guy named Marcus Raynham put together a presentation. He's like Dr. Jekyll and Mr. Hyde in 1996 that talks about firewalls. And he goes, the good things about firewalls, this, bad things this, good things this, good things that. This argument's been going on forever. I just think you need identity, attestation, and then we can talk.
Yep.
Yeah?
Thank you.
Okay.
Okay, so one more real quick.
Yep.
What do you need to help build something like this? What can we do to help?
Wow. I've got a spec. I've got a spec on everything that you saw here. Let's read through it and talk about it. And then I would love to have somebody come in and say, well, here's how we'll break it. Let's break it.
What are the use cases that we could actually put in place?
The use cases that we're deploying in Mount Holly, we call them under the term distributed intelligence. One is VoltVAR management of the new test feeder that we're building, just VoltVAR stuff. Voltage management, Flizzr's there just waiting to be done. The microgrid tends to be sort of just an optimization thing, and that, you know, what are the rules for islanding and reconnecting? Another thing that I'm completely hyped about is external circuit design and tools that suck in the circuit and are smart enough to identify what the pieces are, the components, generate the OpenFMP profiles of what the traffic's going to be, right? The one you cannot get is status. Let's say it's a complicated battery. You know, you can get readings and status at this level here and controls. You can do all that as a standard harmonized. But let's say I really want to get intricate about that battery because something ain't right? That's like a bit string of at least 2048 bits where each bit means something, you know? So at that point, I've got to have I need that thing to publish just a blob. And the blob shows up, and here I need to have a special piece of code that knows how to decipher that SAF battery in order to show what's going on, right? So the architecture, this kind of architecture stuff is there for everybody to start pounding on.
Okay,
All right,
we'll get with you later.
is that it? Thank you guys very much. It's an honor to be here, absolutely.